Hi, my name is Connor, and today we will be talking about Lagrange interpolating polynomials for our class Numerical Analysis in the semester of Fall 2022 for Discussion Section 2D and Lecture Section 1. Let us consider a situation where we have a discrete set of data points. Say, for example, the temperature over a 24-hour period recorded at 3 separate times. While we have the exact temperature at 3 times, what if we wanted to estimate the temperature at some point in between? We could construct a polynomial such that it passes through each of these points, where we could then use the polynomial as a function to tell us the temperature at any time through the entire day. This process, where we create a function that passes through a discrete set of points, is called interpolation. And if we wish to use a polynomial, one way to create this is known as a Lagrange polynomial. Other methods exist too, but for any given set of n+1 data points, the interpolation theorem tells us that there should exist a unique n-degree polynomial which interpolates the set. Therefore, the result of any construction method is exactly the same. To start, we must first create n+1 Lagrange basis polynomials. For each x sub k in our set of data points, we multiply times x minus x sub I, where x sub I is every x in the set which is not x sub k, and we divide this by x sub k minus x sub I, where again x sub I is every x in the set other than x sub k. To create the zeroth Lagrange basis polynomial, we first expand the definition at n equals 0, and we then substitute for x sub 0, x sub 1, and finally x sub 2. We repeat this again for the first and second Lagrange basis polynomials. What is important to note is that each Lagrange basis polynomial, when evaluated at its corresponding node, for example, the zeroth L polynomial at x sub 0, will be equal to exactly 1, while all other basis polynomials will equal 0. This will hold true for every node in the set. After we have our basis polynomials, we then scale them by the desired output values at each node, and then add all together to get our complete interpolating polynomial. In the scenario we presented, we have no way to measure the error without additional data points or some knowledge about the underlying function. However, sometimes this function is known, especially when interpolation is used to approximate a function. Interpolation is often used to approximate a function when reasonable error is desired over a large domain. This is in contrast to a Taylor series expansion, where error grows quickly as we move away from the center point. When interpolation is used to approximate a function, we can express the remainder term for an n-degree interpolating polynomial using the following function, where the product term contains each of the nodes. Of course, by its very design, the product term tells us that the error will be 0 at the nodes, and that maximum error will occur somewhere between these nodes. However, the exact value of psi is usually not known, and so this remainder function is most often used as a bound under certain assumptions. If the maximum value of psi happens to be known in the interval, then the maximum error can be found. This can be done by differentiating the polynomial from the product, setting it equal to 0, and solving for x. Any roots found can then be plugged back into the remainder function to get the error at these points. Compared with other methods, the Lagrange form of interpolating polynomial is easy to construct and understand intuitively, especially for low-degree polynomials. However, there are many downsides when compared with construction using divided differences and Newton's form for the purposes of interpolation. Most notably, any time that a new node must be added, each Lagrange basis polynomial must be completely recalculated. This is in contrast with Newton's divided differences, where only marginal additional work must be done to make the polynomial interpolate an additional node. For this reason, Lagrange polynomials are rarely, if ever, implemented as algorithms, since Newton's method lends itself more easily to efficient computation.